So I said that when we look at further projectile motion, and when we're talking about with resistance now, we can still consider it similar to how we've talked about normal projectile motion. Like how have we approached it? We've looked at these different kind of X and Y components, but what's the other factor that we have to consider now? We have to consider resistance, right? And so typically what you're gonna get is like these kind of long explanations of setting up the question. Because from what I've been reading from these like previous HSC questions, they're not getting you to derive the equations of motions of each time, right? They typically give them to you in some regard. And that's only because I think if they wanted to test deriving the equation of motion, they wouldn't need to do it with resistance. They could just give it to you, right? They could just probably give you like a normal projectile motion question if they wanted you to derive equations of motion. So they simply give you these kind of things, and these should be familiar for. You've got the acceleration equals to minus k times velocity. You've got the horizontal part, and you've got the vertical part there, which has gravity there as well. Okay, so we have these two components, and they give that to you. Typically, from what I've seen, they require questions that you have try and find expressions rather than actual values. So they're asking you to derive results. They're asking you to verify things. And then there is one value here that they say. So what is the limiting value of the horizontal displacement of the particle? But again, you'll notice, right, like this whole thing is like an abstract situation. There is actually no initial angle. They just give you alpha. So when they say what is the limiting value, the value is going to be turned of alpha and g, right? So that's just something to think about when you're answering these. That even though it says value, and we typically attribute that to a number, it may not quite be that, all right? So let's have a look at the first part and see how we can start. So what's the situation? We're throwing something from the top of a tall building, and we want to first find an expression for the horizontal velocity. So derive the result. And again, they're giving you the derivation, like they're telling you that's what it is, right? So I want to write RTP x dot equals to u e to the minus kt cos alpha. All right. Thoughts on where to start with that one?
Just differentiate.
Differentiate what? Exactly. So we have the acceleration, and I want velocity. So which way am I going to be going if I want to go from acceleration to velocity? Because they give you these, right? They give you these parts.
No. What?
They're giving you these,
Yeah, that's what we need.
and you want to derive this first part here. So I'm going from acceleration to velocity, so what do I want to be doing there?
It was like that formula.
What formula? Sorry, yeah, you go.
Like x double dot, you know?
Yeah, yeah.
It's all these things. It's like dv, dx, v, you know?
dv
xv, you know? One,
v dv dx,
yes.
or dv dt.
Yeah.
Yeah, you're right. You got all these different forms. Which ones do you think might be useful here for deriving this? So I'll write these equations down here that we have them too. So we have that x dot is equal to
What is
x and y double dot. Yeah, initial.
So x equals at t equals 0, what b equals to u.
At 2, it'd be u cos alpha. Are you talking about the horizontal component or the vertical component? Yeah. Okay. Okay, so what do you want me to start with here then? We still haven't really gotten anything on the page.
Integrating.
This guy?
Yeah.
How'd you integrate him?
Using integration, actually.
Yeah. So if we want to get x dot.
Well, the x dot dt.
Yes, good. And like I said that this is the solution to this is like a differential equation, right? And the solution is going to be an exponential. I did kind of work out another way that you might approach this. So if you have x double dot is minus kx, we start with that, right? And then we know that that's dv dt. But I guess in this sense, we don't have v for velocity, right? So instead, rather than writing dv dt, you could just write dx dot dt, right? Because it's the horizontal velocity. And then this guy, what I saw that some people do is they actually divide both sides by x dot, multiply both sides by dt. So it looks a bit nicer like this, right? And so this one, if we integrate with respects to t, that's just going to become a constant. And this guy, well, what's this guy? If this is x dot on the denominator and dx dot on the numerator, what's that? That's just a log, right? ln. So we got ln x dot is equal to minus kt plus c. Then you can use your exponential tricks and whatever. So you raise both sides to the power e. That's just going to become x dot, isn't it, if you do that. And then e to the minus kt plus c. But then remember, that should be a power. Like that. But then this guy can just be e to the c, which is just a, right? Initial conditions, what do we have? Yeah, so that's just your like initial velocity stuff, same as normal projectile motion, cause alpha. So then you substitute that in, so you get u cos alpha is equal to a e to the 0, so a is equal to u cos alpha. And then so our final expression is x dot is equal to u cos alpha e to the minus kt as required. Okay. All right, cool. What was part 2? What did part 2 ask for? Verify. So let's go back to the question. Now, with verify, I think it's a weird one because I haven't really seen that all too much when you need to verify something. So, you know, when I say that when you're required to show something, you should never assume something is true. The verify term kind of makes me think you could assume it's true and then try and show not only that it satisfies the equation of motion, but also the initial condition. And what's the initial condition there? What's y dot? Because you're doing vertical velocity now, u sine alpha, right? So just keep that in mind. What did you guys do for this one?
Just show that that's it.
Yeah. Did you integrate or did you? Yeah, because another method, because when you say verify, if we're assuming that you're allowed to assume it's true, one thing you might want to do is you could also differentiate this expression and show that you get this up here. But I mean, and actually when I did it, it was actually a bit trickier. So like, it's actually longer. So yeah, so we might as well just integrate if we're going to do it like that. So yeah, so what did you do when you integrated? So you started off with this guy? Yeah. So it's part 1. So part 2, verify y dot is equal to, what was it? Let's just bring it back up. 1 on k u sine alpha plus g. It's not the nicest expression, eh? I do all the brackets right. Yeah. Also, I've been using capital U. I don't know. I usually use that. I don't know about you guys, but that's why bad habit. Yeah, little U's don't do it for me. All right, cool. So what did you do? You integrate this guy. So we start off with this y dot equals to minus ky dot minus g. Where did you go from there?
dy dt.
Yep.
Do the thing.
Julie.
Julie do the thing.
So multiply by dt, divide by this. Is that what you're thinking?
Yeah.
Yep. And also, like with the negatives here, you might actually want to factorize that out. Yeah, because it makes it easier when you're doing the log integration here. So I might do that just to be really clear. So it's plus g now. And then so dy dt, divide, so we get ky dot plus g.
We need k at the top.
Yeah, so we need k at the top. So, because I want my log integration, like that, so you did, to undo that, and then we can integrate both sides. So in this side, I'm going to get negative t plus c, and this side, I'm going to get ln of ky dot plus g. Oh, 1 on k, yeah, thanks. And so k rho, ooh, what do you do next?
C.
What's that?
I found C now.
Okay, so
I don't know, I always found C on one.
yeah, that's fine. You can do that. So you find C. So at t equals to 0.
You can't do that, I guess.
Yeah, there's nothing wrong with it. As far as I know, y dot equals to u sine alpha. And so, how's this going to work out? Is it going to be nice? Is it going to be nasty?
Oh, it's not beautiful.
Yeah. I mean, look at what we're working with here, right? So k times u sine alpha plus g equals to c. Yeah, that's nice, isn't it? So then we get 1 on k ln k of y dot plus g equals negative t plus 1 on k ln ku sine alpha plus g. What did you do next? Log, yeah, okay, so
it'll be...
did you take that to the other side, or what did you do? Or would you multiply by k?
Mine did the letters.
Wait, what? What did you do?
Oh, it's very, very, very similar.
Did I do something wrong?
No, it's fine.
Oh, okay.
It's the same thing.
Yeah.
You can just put the one on the other side to be 1 on k and then ln of k y dot plus g on top of...
Yeah, okay, so you take it to the other side, it becomes a subtraction, and then you use your log laws. So log law is really important here. Then you use your log laws to make it a division. So 1 on k...
Oh, you can also put k the other side. Oh, but as soon as you get over there, then multiply.
We're doing a few steps at once. So let's just multiply by k first, then, maybe. You want to do that?
Yeah.
Okay, I'll multiply by k first. Both sides by k, so minus kt. And then you want to do that log subtraction rule. So k y dot plus g all over k u sine alpha plus g. Right? And then you can use your exponentials. So, because you want to get rid of this. Because what are we trying to get? We're trying to get y dot equal to that, right? So this is not quite there, hey? So k y dot plus g over k u sine alpha plus g. Oh, that's meant to be under the fraction. Yeah, don't do transcription errors, guys. Minus kt. And we're pretty much there, so just multiply it out. Yeah, ku sine alpha plus g e to the minus kt. And then we can do this in one step, so that's, can I do it in one step? Ku sine alpha plus g e to the minus kt, take away g, outside of 1 on k. So, yeah, you can see, right, it's just combining all your knowledge of your integration strategies and then just rearranging it, log laws, evaluating constants. You guys have done it before, so.
It's not that much worse than without resistance.
It's actually, yeah, it's pretty approachable, right? It's just being aware of what to do, I think. Like, especially when I read through a lot of these solutions, it's like, oh yeah, I understand that. But then it's like the pressure of the question, they always find different ways of doing things. Like in your exam, you had ones with collision, right? So they may find creative ways to adjust it, like maybe the particle starts doing different things along its equation of path. But yeah.
So it's stop midair and just...
Something like that, right? Do particles do that? I don't know. You guys do physics, so